Here I am. Nice.
Okay, everybody. Thank you all for coming to today's quantitative seminar series. I'm Cole, one of the Coles, and I'm also one of this year's organizers of the quantitative seminar series. I'll first begin with a land acknowledgement. The University of Washington acknowledges the Coast Salish peoples of this land, the land which touches the shared waters of all bands and tribes in the Suquamish, Tulalip, and Muckleshoot nations. We also acknowledge that we live and work on the ancestral lands of the Duwamish people, the first people of Seattle. Now to introduce our speaker, Cole Monohan. Cole is a quantitative ecologist that uses statistical models to inform issues in marine resource management. He currently works as a stock assessment scientist at the National Marine Fisheries Service, NOAA, at the Alaska Fisheries Science Center in Seattle. His work mostly focuses on the Gulf of Alaska pollock assessment and research on assessment methodology and development of Bayesian capabilities for fisheries models. Cole will take questions as we go. And for folks online, if you just raise your hand, I can unmute you, or you can use the chat and I'll read it out. But yeah, thank you everybody for showing up today. And with that, it's my pleasure to turn it over to you, Cole. Thank you.
Yeah. Thank you. Thanks everyone for coming online and especially in person on a beautiful day. Yeah, I guess I'll start by just noting my collaborators, Jim Thorson, who works with me at the AFSC, Casper Christensen, who's the mastermind of TMB, as probably most of us know, and then Bob Carpenter, who's working with us. He's kind of part of the core STAN development team, and kind of a stats and programming guru. So yeah, please feel free to interrupt. I hope this is really free form and casual. So I'm going to jump in. I have a lot of meaty material to get through, so I'm going to kind of zoom through the intro. But basically, we're all starting to do TMB now, where ADMB is sunsetting. As a community, I think Quantitative Fisheries is basically settled on TMB as our modeling platform of choice, especially for stock assessments. So SAM in Europe, WAM on the East Coast, FIMS is kind of like a national thing, but also bespoke. So at the AFSC, we're starting to kind of bridge over from ADMB to TMB, but also data processing and research. So VAST and SDM TMB for like spatial index standardization, GLIM TMB for kind of like regressions, DSEM's a package we're starting to use more frequently for like time series and causal models. And TMB uses maximum marginal likelihood via something called the Laplace approximation. And it does that super efficiently using sparsity, which is a big theme of the talk for today. But just high level, I think if you're here, you probably agree that it's useful to do both what some people call frequentist and Bayesian inference. And in my mind, we should just be able to toggle back and forth between the two. And I'm going to leave it at that. We don't need to discuss and argue about the philosophies and differences. So, Bayesian inference can be useful if you want management quantities to be as probabilities. Some argue that you get better uncertainty estimates, and also can be a way to check some of the assumptions in your model. If you're a Bayesian, the Laplace approximation can just be seen as a quick approximation when you're building your model. If it takes a couple hours to run your STAN model and it takes a minute to run Laplace approximation, you can use that in kind of the early stages of development of the model. So the point being that we can toggle back and forth, and it's nice to have a tool that does both really efficiently. And I'm going to make a case today that TMB is that tool. So hopefully I can convince you of that. Yeah, so kind of moving on, if we're going to do Bayesian inference, so TMB already does frequentist inference exceedingly well. That's why it's so popular. We want to do Bayesian inference equally as well as possible. And I think as a community fishery scientist, we're basically wedded to autodiff. Nobody's using JAGs or things that don't have an autodiff backend. This is basically TMB, ADMB, or STAN. There's like some Python and other equivalents, but I won't talk about those. So NUTS is basically works really well if you have an autodiff backend. This is why it's great for ADMB models and TMB models, and why STAN uses autodiff as well. STAN being a piece of software named after a person, Stan. And so NUTS is an MCMC algorithm, and it scales really well in dimensionality, right? We can push it up to 10,000, 20,000 parameters. It works quite well on hierarchical models and has some other nice features. And I've kind of, over the last almost decade, have been making a case that we should use it in our field. So Casper and I put out a couple R packages back in 2018. TMB Stan is designed specifically for TMB models. 80 nuts was designed originally for ADMB models. And yeah, so that's kind of what's available now. And I've kind of also been making a case for it in Bayesian fishery stock assessments, which we won't go into details. So since we're going to talk about nuts, I did want to pop over, and hopefully this works. So what does nuts look like? So nuts, when it runs, it's creating something called a trajectory, these different trajectories. And that's what these kind of squiggly lines are. So this shape here is a contour showing some posterior surface. In this case, it's 2 dimensions, and it kind of looks like a banana. I'm going to switch this over to, efficient nuts. And so these, each kind of time it clicks over, it's creating this like squiggly line that's called a trajectory. And if we switch over to something called a standard, which they've got built in here, this is just like a bivariate standard normal. This is as simple as you can get to sample from. And the point I want to make here is that these trajectories, what a good trajectory is meaning that it can kind of go from any place in this posterior space to any other place with very few steps. Each step, each point on each trajectory is an expensive computation, so we want to minimize that. So basically, the length of these are roughly proportional to efficiency, how long your model takes to run. So let's look at like a really crazy model. And I think if we get rid of, let me remember how to do this. And you can see here, this is quite a crazy, crazy posterior. So you can see it kind of gets stuck down here. And a difference here is that if we look, let's actually look at this donut one. So one behavior we see is occasionally we see these ones where you have these like kind of wiggles, right? Where it's going kind of swerving back and forth. That's really long. That's inefficient. So that's what a trajectory looks like. And so what we're going to be doing today is talking about a method to make those trajectories faster and easier to compute, basically. So if we have, these trajectories are exploring that posterior well, we have low autocorrelation, high effective sample sizes. And then what the metric I'm going to use today to talk about is something called efficiency, which is the minimum effective sample size per time, right? So you want that to be high. If you can get 1,000 samples in 1 second, that's a lot better than 1,000 samples in an hour or a day. So we want efficiency to be high. Yeah, and so likewise, to reduce the run times, we want these good nuts trajectories that are computationally cheap. And that's what we're going to do. So nuts is great. It works with a ton of models. It's probably the most popular Bayesian algorithm in applied statistics today, most likely. And it's applied on a ton of different models. But it kind of does have an Achilles heel. And it is something called global covariances. This is what we're going to talk about a lot today. And this is when you have marginal variances, kind of linear, like a global scale, meaning the whole posterior, and high correlations. So that's what I mean by covariance. It's a covariance matrix kind of of the global shape of the posterior. And I'm going to show you an example of why that kind of breaks the efficiency of this algorithm. And so the big challenge is that this algorithm has that Achilles heel, and we don't really or typically know what the global covariance is before we start running the model. And so nuts and Stan in particular has something called a metric, which counteracts and improves sampling. And so you specify this when you run Stan, you could call something called diag_E. And this is going to account for scales. And this is the default. If you've ever run Stan, this is the metric that it's using. This is diagonal metric, and it's tuned and estimated during the warm-up. You can estimate a dense one, and I'll explain what dense and diag are in a second, and this will account for covariances. But first, let's look at what happens. So this is a blatantly simple model. This is a bivariate normal. They're independent. So x1 is standard normal, variance of 1. The second dimension has a standard deviation of s. So the question is, what happens to Stan runtime as we just increase s off to infinity? So that's what's on the x-axis here. So this is in log, both of these are in log 10 space. So I want you to focus on this red thick line. This is the total runtime. This is like if you were sitting in front of your computer, how long Stan would take to run. And as you can see, even for a two parameter model, if you really crank it up and exaggerate it, you can get really big increases in runtime. The other observation to notice, this dashed line, this is the amount of time it's in warm-up. So typically the first half of the chain is warm-up and the second half is sampling. And you can see that when we, in these kind of extremes here, maybe I can use my laser pointer. Basically, the total is the sampling plus the warm-up. And so we can infer when we're out here that 100% of the time is in warm-up phase, right? So that's just one way to read this plot. So that's none here. This red color is like this kind of default Stan behavior. And I'm going to introduce two new metrics, I call them, called diag and dense, and those are both basically working really well. They're invariant to S, right? That's good and what we want. So why is that so slow? So this is iteration on the X. This is taking one of those really big S's. Trajectory length. This is how many evaluations of the gradient we have to do for every iteration of the MCMC algorithm. So high is bad, right? Those kind of wiggly things we saw, we're talking like 10,000 points to get from one place in the posterior to another point. That's horrendously expensive to calculate. But you can see it's really high for a period and then it drops off a cliff and comes back down to reality. And that's because Stan, after running the model for a while, has learned that S is big. It now knows that there are differences in scale in the posterior, and it can sample efficiently. That's what the warm-up period in Stan is doing, is learning the variances, the marginal variances of your posterior. And so this is really typical when you run Stan. If you plot this kind of output, you'll see it's really expensive at the start, and then it kind of figures it out and works a lot better. So let's switch to correlations. So same thing, super simple model, bivariate normal. Now the variances are both 1. There's no scale difference. That's easy to sample from. But now let's take a correlation and send it to 1. And this is a really stupid x-axis. It's like logit of the correlation. But basically, this is like going off to 1. This is like 0 over here. So the same thing, we could see this total runtime, it just goes way up, right? I mean, orders of magnitude. This is a super simple bivariate normal model. Stan should be able to sample this trivially. And in this case, we could see something different happens where the warm-up is equally slow as the total, meaning that the warm-up and the sampling periods are both really slow. And that's because if you have a diagonal metric, it cannot account for correlations. And I'll show a visual of that, why that is in a second. And that is to say that Stan's algorithm will not rescue you from big correlations in your model. And likewise, this dense metric you can see is invariant to the correlation. That's the behavior that we want out of our sampler. And that's what I'm going to introduce and show works well. Yes, please interrupt.
Why would you ever do the diagonal then if the dense seems to do the same equally as well in the figure before?
2 slides later.
Okay, cool.
I think we have.
Yeah, please,
question.
questions. Yeah.
Andre.
This is like super heavy stuff, so please.
Is your volume on?
Yeah, it should be.
Andre, can you ask your question?
Not hearing you, Andre.
The mute see wave that's coming from your speaker, from the projector. Like go to the sound in the bottom line.
Sound in the bottom.
Yeah.
I mean, this is what I have.
Click that thing. Speaker. Yeah, do that.
Okay, try again, Andre.
And then try.
I think he's on mute.
He's muted. At least one of his accounts is muted.
Andre, unmute. Yeah. Okay.
Can you hear me?
Oh, now it's coming. Yeah, hold on. Let me turn it up. Why will they not let me increase the volume? Okay, try again, Andre.
Yeah, can you just, I mean, maybe I missed it, but, and maybe you're going to talk about it. Remind us what the difference in dense and metric and diag actually are, because I think maybe I've lost that. And are you going to talk about that, or did I just miss
My
something?
next slide, yeah. So the only point I was trying to make about previous slides is that correlations are bad and big differences in scales are bad. And that affects the ability of Stan, or the NUTS algorithm in general, to sample from your model efficiently in really profound ways. So let's dig into what these metrics are. So we're going to do some math. So here I'm going to have, as an example, I'm going to have a bivariate normal. Again, we're keeping it really simple to illustrate, but this is going to scale into, into higher dimensions. So now we have this covariance matrix. So it's going to have a correlation of 0.98, so pretty correlated, and then a variance of 1 in 100. So x1 is basically standard normal range, and then this one you can see the range is bigger. So they have differences in scale and they have a high correlation. Okay, this is X. This is our parameter space. This is just like some random, these black points are random draws. This ellipse is kind of like a 2D bivariate standard normal. And so the black circle is going to be the same across all these plots. And so what we want to think about doing is like, let's rotate our parameter space and try to get rid of the correlation. And in math, kind of more broadly, you do that with something called a Cholesky composition.
Sorry, which is the red dots?
So X is like your model. That's what you're used to. That's
the circle. Is that the truth? Or is that the...
It's not truth. It's a reference point. It's not a reference point. It just gives you perspective on the dimensions and shape of the posterior. The black circle is what we want our posterior to look like. And here you can see it doesn't look like that. Okay, so yes. So what we're going to do is we're going to define a new posterior space, and I'm going to call it Y throughout. So basically, we're taking this L inverse, which is a matrix, and we're multiplying each posterior point by this L. And this is a rotation. This is really common in statistics to do. And L here is the Cholesky decomposition of a matrix M, typically called the mass matrix in the Hamiltonian Monte Carlo literature. And the property of L here is that if you take L and you multiply it by its transpose, you get M back. It's kind of like a multi-dimensional square root, right? If you want to take the square root of 100, it's 10 times 10. So you just kind of multiply the thing. And so it's essentially like a square root. It's like a generalization of the square root that applies to matrices. And so what we're going to do is choose M and then calculate L inverse and multiply X by that. It by X, I should say. So I'm going to call this a none matrix, or sometimes I call it a unit matrix. So if we just take M to be the identity matrix or the unit matrix, L inverse is just still identity. It doesn't do anything. So the multiplication does nothing. You, of course, wouldn't ever do that. But now here's a more interesting case. Let's just take the variances from sigma, right? So ignore the off diagonals, ignore the correlations, the covariances, and just look at the variances. Now L inverse is diagonal. I also should say that this is always 0. The upper diagonal triangle is always 0 in the Cholesky. And so when we do this multiplication, we're essentially just dividing by the square root of the variance for each variable. That's how you get rid of a big variance, is you just divide by the variance, right? And that's what the diag metric is doing, is it's just rescaling. It's squishing the axis. So you can see that here, right? We went from -30 to 30 to -3 to 3. So now they're on the same scale, but we haven't accounted for the correlation. So now if we use what I'm going to call a dense mass matrix, so now we have the covariances in there. If I just put sigma in and calculate L inverse, I get this slightly more complicated matrix. And now when I multiply Lx by that L inverse, I've decorrelated the parameter space. And so the dense matrix is going to handle the correlations and the scales. A couple other observations. So this diag will account for scales, and it only does element-wise multiplication. So computationally, it's almost trivial to do. This one will account for scales and correlations, but is a matrix multiplication. And so that can be expensive and as dimensionality increases. And so this is why when you run, so Stan is doing this one. This is why when we had a really big correlation in our really simple model, Stan really struggled to sample from it. And why, if we go back, this dense, this blue line is essentially invariant, because if I make the model have a big correlation and then tell Stan it has a big correlation, it can sample equally well as if it had no correlation. That's the whole point of this talk, is that we can decorrelate and descale the posterior before we sample, and it will be more efficient. And this is not something I created. This is, known in the stats literature, and this is what they do.
Maybe you're probably going to get to this, but like it seems like that's all very well and good and obvious. But how do you know what the correlation is before you've done the?
Yeah. Okay. I love this audience. You guys are just like. It's such a great community. Awesome questions. Yeah, I'll get there in a second. So this is an old figure. I'm really sorry. I lost the code to reproduce it. So it's like flipped and renamed. But the point is that this is X from the previous slide. Here's the identity, the diagonal, and the dense. So focusing on this far column, look at the differences in the trajectories. This is a very small correlation too. And you could see in this bottom right, these trajectories are moving along the correlation, kind of along the shape of the posterior better. These, when I say a good trajectory, this is what a good trajectory looks like. These are bad. They're going back and forth and squiggling. Yeah, so that's the basic idea, is this is Y space. We want to sample, we want the algorithm to work in this Y space. This is easier to sample from than this is. And the implication, the consequence is that we have better sampling here than we have here. And the model takes a lot less time to run.
Wait, I have an actual question.
Yeah.
So no U-turn sampling takes advantage of the Hessian though, and like of sort of the shape of the likelihood better than metropolis spacing or something. And so can you, like, what is no U-turn sampling doing that metropolis spacing isn't? That this is like, how is this a step past?
Yeah. So it does not use the Hessian. It uses the gradient. There is a version that uses the Hessian called Riemannian manifold, I think it's called. It's not widely used. Exactly. And that's how it makes those trajectories, is that it's using the gradient to kind of, it's like a ball. One of the analogies is like a ball kind of rolling in a valley. It's like why you see those. So why you see these like squiggles. Like if you threw a ball, it would kind of go like a snowboarder on a half pipe or something. So that's what it does differently than other previous algorithms. It uses the gradient, but it's not using the Hessian. We are going to use the Hessian in a minute though, so I will extend that. Okay, so dense is just better, right? So why not just adapt a dense matrix ahead of time? It's really a chicken egg problem. It's really hard. It's really easy to estimate one covariance term in a matrix, but if you have 100 parameters, 1,000 or 10,000, just think of the dimensionality of that, right? That's going to grow like, what is that, n squared over 2. So that's bad. And so basically, by the time you have enough samples that you can estimate that dense mass matrix, that M, you already have your posterior. So you don't need to use a dense matrix. So it's a bit of a chicken and the egg. In order to have it, you have to run your model long enough. So it's basically never used in Stan, as far as I'm aware, maybe on like really low dimensional models. And so what does the Stan manual say? All parameters should have unit scale and be no correlation. The onus is on you to parameterize your model so that you don't have those things. And I think if you come away from one thing from this talk, I want you to understand this sentence in the Stan manual and why that's in there. It's buried in there and it gets thrown around in the forums a lot. And this is why, because this is harder to sample from than this. And so try to get rid of the correlations in your model. And that's really good advice. We should all do that if possible. But we just can't do that. Sometimes correlations are inevitable. Like the SPDE models are classic. Like if you have two random effects representing like density in space, if they're close together in space, they're gonna be correlated. That's like how they're defined. And we'll see an example of that in a bit. And then other times it's like, well, we don't have access to the source code, or we just don't know how to do it. And so we can't do that. Okay, so how about, what's another option we could do is we could use an approximate dense metric from before we start. And this has been known for a long time. The classic Delman Bayesian data analysis book talks about this. Take your Hessian at the mode, invert it, and use that. And that's what A and B has done for like 20 or 30 years. And that's why A and B actually was quite good, and still is quite good at doing this sampling. And if you've used my package 80 nuts, this metric equals MLE, that's what it's doing. It's using the Hessian to calculate a dense mass matrix, doing that rotation and sampling in that space. That's what my PhD was. That's what I did, was like modifying the A and B code to do that. But for hierarchical models, we have a problem. We can't invert the Hessian because there is no invertible Hessian for hierarchical models. They don't even have modes. The mode is the variances going to 0 and the random effects being constant. And so this is why you can't just optimize. Typically, you can't just optimize a joint model, hierarchical model. This is why we have a Laplace approximation. So there is no joint model. The other problem is that this, L times X, I should also put another L on there too. We'll get to the calculations in a second. Scales poorly with dimensions. So if you have 10,000 parameters, this is a big matrix. That's a lot of calculations to do. So it doesn't scale well in dimensionality. Okay, I think I need to speed up. Okay, so we do have a solution. Casper has a solution. The stats field has a solution that Casper has coded for us in TMB called the joint precision matrix Q. So for those of you who have used TMB, what happens if you AD report a non-linear function, any kind of function of some fixed effect in your model? How does it, you get a standard error in SD report, right? It uses the delta method. This is the formula for the delta method. This is the standard error of this parameter, whatever parameter, theta. And then this is the square of the derivative of the function, right? So if you want to, if your function is, if phi is theta squared, this would be 2 theta squared. So you're basically multiplying these two terms together. So it's the standard error of theta times the derivative essentially of the function. And then this is there's like a multivariate version of it that uses it's the same idea, but just vector. But importantly, you can do this in TMB and you can stick a random effect into your function. Spawning stock biomass is a function of random and fixed effects. Your recruitment deviations are random effects. Basically, every parameter in your model goes into into SSB, right? So how does TMB get a standard error for SSB? It uses something called the generalized delta method. And the key here is to note is that we now have random effects U, and then we have this V term. This is a covariance matrix of random and fixed effects of the joint posterior space. And that's, I'm not going to go into too many details because we're out of time, but that's exactly what we want. There's some details, I think we should invite one of these two guys. I think it's Nan Zhang and Noel Cadigan to come and talk. You could have a whole seminar just on Q and how this is calculated. I'm going to call this joint precision Q. I think we have to skip it. I will say that you can get it from from TMB and the SD report like this. It's not returned by default, so you set true, and then you just extract it from the list that comes back, and then you have access to Q.
This is a TMB function.
This is a TMB specific function. I don't know of any other software that does this. And the coolest thing, let's look at some examples. The coolest thing about Q is that it's sparse, meaning it has a lot of zeros in it. This is kind of a weird plot. So the upper, splitting this by the diagonal here, the upper triangle here is just Q, and I'm just plotting a color if it's non-zero and white if it's 0. So you can immediately see that almost all of this Q matrix is 0. The sparsity is like 98% or something, highly, highly sparse. Now, if we invert Q, we get a covariance matrix. Q is a precision matrix. If we invert it, we get a covariance matrix. If I convert that then to correlations, that's what you see on the lower triangle here. Totally dense, not a single zero in sight, and a ton of correlations. This should boggle your mind that this matrix on the upper triangle encodes the exact same information as this crazy dense one in the bottom triangle. That's a miracle to me. And so TMB uses Q because it's sparse and it makes everything fast. All those generalized delta method calculations fast. Here's another one for a state space stock assessment model, a WAM model, which we'll look at a little bit more later. Same thing. Not quite as much sparsity, but quite a bit, and then a lot of correlations and a lot of, it's very dense. That's what, when I say dense, it's like no zeros in it. Yeah, please.
That does boggle my mind. Can you give me some intuition for why you code all of that information with so much?
Oh yeah, I'm supposed to repeat the question. So how is that possible, basically? And so the short answer is that elements of Q, the precision matrix, encode conditional dependence and independence. When you invert it to get the covariance, an element is encoding marginal. And so they're representing different things. And so this conditional independence, this is what TMB is really good at detecting is, if you, which parameters are independent of each other.
So if they're representing different things, how is it?
But you can get to one from the other.
Yes, you can do it numerically or mathematically. It's just the inverse.
You're not really.
But I thought that was the inversion was the problem when you have lots of parameters.
So this is not the Hessian. It's carefully called the joint precision matrix because it's not the Hessian at a mode because there is no mode, but it's trying to be that. You can think of it like that loosely. But yes, I literally just took R and said solve Q and then cove to core of M and plotted, just fuddled around and plotted it. So this is, Casper worked this stuff out a long time. This has been in TMB the whole time. It's behind the scenes and nobody thinks about it or knows about it. But Q, joint precision Q, it's fast to calculate. And really importantly, it's sparse, meaning it has many zeros. Let me reiterate a point. If I took M here in the lower triangle and I inverted it, I would get Q, but all these white squares would be really, really, really small numbers because of numerical issues. When I say it's zero, it's identically a zero. It's a mathematical zero, not like an approximation of a zero. So you actually can't go back and forth between the two. You'll lose sparsity when you do that. Not an important point, but okay. So let me get this out of the way. So TMB, that is if you've run a TMB model and if you've used output from TMB, you are assuming that your model, the joint model, the fixed and random effects, has a normal distribution of zero. Well, not zero. That should be the MLE, the joint mode, and sigma is the covariance. That's what you assume when you show people output from a TMB model. So I'm gonna hypothesize here today that 5 things: that there are a bunch of correlations in hierarchical models, and this is a problem. And 2, that this M or Q inverse or whatever approximates that global covariance well enough, and that we can use M either as a diag, dense, or what I'm going to call a sparse metric, which I'll derive in a second, and that these, what I'm going to call pre-metrics, eliminate the need for this expensive adaptation in STAN. And then basically it's better. Okay. What am I doing for time? I think I'm okay. Yeah, so
You do have to fit the MLE though to get it.
yes, you do. Yeah. So this just conditioned on that you have Q estimated. And great point. I'll come back to that. Did I answer your question about, yes, you have to get Q and that's how we know it. So this is something we know it ahead. Before we start sampling, we have Q. That's an important point to highlight and reiterate. Thanks, Q. Okay, so here's some just models I pulled. Dynamic linear model, causal model, a Pollock stock assessment, GLIM TMB, SDM TMB, and a WAM. This is a state space stock assessment. So some kind of fisheries adjacent models. They're a couple hundred parameters at most, so not really big. Sparsity here, percent zeros in Q, you can see it ranges, from 92 to a low of, 29 or so. And then here, maximum of absolute pairwise correlations. This is kind of like the bottleneck that you're going to have in your model. This is the highest correlation between any two dimensions in your model. And they're big. They're really big for some of them. My Pollock model's atrocious. But even WAM is pretty high. These causal models, like these correlations are high. High enough to cause problems. And then here's the same thing for the scales, which I won't talk about. That's all I want you to get from that.
Can I ask one question about that?
Yeah, totally.
Linear correlations.
Yeah.
Okay, and the other thing that I want to hear you talk about maybe not all the time is how you personally think about and visualize the shape of your models. That's something you'll get to later.
Yeah, the question is are these linear? The answer is yes. And how do I visualize them? And I will get that to a little bit later. Yeah. Okay, so I'm kind of walking through these hypotheses. So Q is fast and good approximate method. Kind of the gold standard right now in the Bayesian statistics literature is something called variational inference, which I don't understand at all, but it's trying to do the same thing. So I'm comparing these, and I'm going to zoom through this because it's not super important. But basically, the blue points here are closer to 1, and that's good. And so we're beating TMB, TMB is beating state-of-the-art statistical algorithms. It's a better approximation, and it's like a 10 to 100 times faster. So what I conclude from this slide is that Q does a pretty good job approximating the joint geometry of the posterior. And so then if we just take random normal draws from that, we have a pretty good approximate posterior. And in fact, we can initialize our nuts chains from that and do other things. You could do simulation. You could do like parametric bootstrapping. That's how you would do it in TMB. And I highly recommend doing that. It's a really nice tool to use in TMB. Okay, so cruising through, let's go back to full sampling with nuts. Yes, Trevor.
So having done this first step to get Q, you basically now have the posterior.
You have something that
you need the next step actually getting the posterior by using nuts.
Yeah. So
how fast is it to do get Q versus do nuts?
Yeah. So the question is, if Q is a good approximation, do you need to sample? And the answer is sometimes not. And that's one of the points is that even if you're a Bayesian and you don't care about frequentist statistics and you abhor them, you still can use that as an approximation when you're building your model because you can get pretty close for approximately 1% of the runtime, 1 to 2% of the runtime. So yeah, it's a great approximation tool. And that's essentially when you do parametric bootstrapping from these models, you could take Q, invert it, do our multivariate norm, push it through your model, and that's parametric bootstrapping. That's essentially using an approximate Bayesian posterior. Highly recommend, totally useful tool for us to have. But sometimes you want to run full nuts because sometimes it doesn't work that well, caveat, and you don't know until you run it, actually, is part of the problem. Okay, so let's derive a sparse metric. So I'm going to get a little bit deeper into the math of this rotation a little bit. Same picture as before. So X is our silly contrived example. Y is the space we want to sample in. So here's my little box. So what do we have? We have a joint model object, OBJ, for the TMB folks, and parameter vector X. And we have an estimate of Q from SD report. And we have some X zeros, the initial values for the chain. And we have what I'm going to call Fx of X, to represent, this is the log posterior. This is the negative of our negative log likelihood that we report. And then the gradient function, the same for the gradient. So G for gradient, X subscript here is representing, it's the function and gradient in this parameter space. So what do we need to do to run this sparse nuts? We take X0, we map it, we basically take a point here. That's our initial value for the algorithm. We're going to map it over to here. And then we're going to calculate the height, F, of y and the gradient g y. And so that's what Stan uses. It uses f and g to calculate all of everything that NUTS does, unless you're using a Riemannian metric, but nobody does that. And then after it's done running, we have posterior for y, but we really want it for x because that's what we know how to interpret. So we just back calculate to get x. That's it. So the key is, how do we get fy of y? What's the height at this point, and what's the gradient at this point? So that's what this over here is. So unfortunately, before we had L was just the Cholesky of M. Here we have the inverse of M. So that's the key difference here, is we're not going to invert Q. We're going to use it directly. And it's a general property that you can't just invert L and they won't match, right? So L inverse is not equal to, so this doesn't hold. So we have to do some tricks, basically. We have to do some fancy reordering. It's not fancy, it's simple, but maybe unexpected. So we're going to define this thing called J. It's a matrix, the same dimension as your parameter space. And it's kind of like the identity matrix, but like going down the other diagonal, right? So they're just all zeros, except this is 1. It has some interesting properties. The transpose and inverse are all equal. If we pre-multiply a matrix by J, it's going to reverse the rows. And if we post-multiply, it's going to reverse the columns. So it's just reordering the matrix. It's not changing anything else about it. Okay, so again, we're going to, basically we have to like reorder in the rows and columns and then take the Cholesky and then undo the rotations. That's basically what's going to happen. So we're going to take L as the Cholesky of J times Q times J. So it's now all rotated, it's reordered. And then we're going to take that L, undo the ordering, deorder, if that's a word, and then take a transpose. And I'm going to call that L tilde. And that becomes kind of the main matrix that we're going to use to do the rotations. So the question is, whose brain works like that? Well, the real story is, I was having beers with Jim, and I said, what we really should do for TMB is figure out how to do that. And then he came back a couple days later, and he's like, I figured it out. So it's even worse in code, by the way. It's a mess. We could look at it later if you want, but this is like, so this like rotation, this reordering thing is known in the linear algebra world, I guess. It was certainly new to me. I don't really deeply understand the calculations, but the short answer is it comes out the same. Yeah, it's pretty cool. This is like the only novel thing that Jim and I have done. Jim did this bit. I did all the coding basically, and then Casper did all the TMB stuff. Those are the 3 pieces that are going to go into this. This box. This was the hard part. This was the bottleneck for us. Okay, so what we wanted, remember, from this box is fy of y. Well, okay, that's f of x. How do I get x? So I know y is L tilde times x. So if I just pre-multiply by L tilde inverse, I get L tilde inverse times y is equal to x. So I can take, that's how I go from y to x, is I pre-multiply by the inverse of L. So I can go back and forth between x and y, just rotating, derotating, etc. So this is basically x, right? Same thing for the gradient, which is the gradient of f. So I just stick, this is x. So now I have fy of y and gy of y. That's it. That's the sparse metric. With some very careful and clever implementation in R code using the matrix package, dealing with sparse matrices.
Oh, sorry.
Oh, you have a question, yeah. I need to speed up.
Hi, Cole. Can you guys hear me?
Yeah, sounds like Mark.
Oh, it's Darcy.
Yeah.
Close. Hey, so I'm just wondering, when you do this transformation and then pass this along to the Stan software, is the Stan software dealing with the Jacobian of this transformation internally? Thanks.
Yeah, so the question is Stan dealing with the Jacobian? And that's what this part here is. This is accounting for the rotation. It's not a Jacobian. I guess it's like I guess it's a multivariate. Is the Jacobian the multivariate? Quorum students, is the Jacobian the multivariate chain rule? I think it is, which is basically what this part is accounting for, is that rescaling and change in volume. And so that's what this, so if you didn't have this part, Darcy, you would be, yeah, it would be wrong.
Yeah, awesome. Thanks, Cole.
It is indeed, yes. Sorry, Darcy, thanks. The good question though. Yeah, and that just kind of pops out of the, if you think about the chain rule, if you differentiate this thing, it kind of pops out as a constant, right? It's a chain rule in multiple dimensions, the Jacobian. Okay, so yeah, okay. It's the same, it's great. We hypothesize that it's better to do this sparse one. So let's test it. So I'm gonna start speeding up because I'm running out of time. So this is a SPDE, sorry, a spatial model, stochastic partial difference equation, whatever, like the endless style models. We're going from like 100 to 10,000 parameters. Here's the cost of the gradient only, sorry, the rotation only, relative to nothing. And so what we see is that dense scales poorly. This is scaling poorly, right? Diag, which is that element-wise, it's much simpler, is kind of down here. It adds a little bit, but not a lot. And then sparse is in between, except at lower dimensions, like less than, say, 100, 200 or 300. There's some overhead in the sparse matrix representations. But the idea here is that this is scaling really well. And this is what we want, right? So that solves that second problem. So now we know Q ahead of time, and it scales well in dimensionality, meaning that we can apply this for really big models. And interestingly, for this model at least, this is if you include the model gradient, so gx of x. So at 10,000, dimension of 10,000, the gradient call is about 10 or 15% more expensive. That's really low to get a decorrelation of your 10,000 parameter model. That's cool. Okay, I'm going to define the sparse nuts algorithm. Maybe I won't actually, because we should speed up and we've kind of gone through this. I'm going to skip it. Let's do some more benchmarking. So here's simulated models. Now we're going to look at efficiency. That's what we want high, again, relative to basically stand defaults. So we want big numbers. Here's GLIM-TMB up to, I don't know, 500 or 600 parameters or something. It's 30 times faster. 30 minutes to a minute. SPDE, same, up to 5 or something thousand, roughly 20-ish times faster. So it's working and it's scaling. And sparse is staying higher, particularly in higher dimensions.
So high is good.
High is good. Yeah, this is how many times faster the model is to run. And so sparse, you can see, is working really well. Here, this is VAR, vector autoregressive. This is kind of like a time series, multidimensional time series model. It's worse. And we can pop up here and look, it's because min ESS is the same. We didn't need to decorrelate, basically. So we did all these extra calculations and they didn't bias anything. So it's working. Let's look.
Where's dense in that previous one? In the middle?
The,
SPD.
yeah. Okay. So the question is, where's dense in the min ESS? So sparse and dense are identical mathematically. So you get so they're on top of each other. So dense is behind sparse in that case. But they do take a little bit, the runtime is different. That's why the efficiency is different.
What if your Q isn't a good representation of your
I have an awesome slide showing that. Okay, so let's look at some real models. So I've been going crazy on these models. Like I've been pulling them from the stand papers that are like kind of like, oh, these are hard to fit. These nuts really struggles with these models. I was just like, let's throw that at it. Let's throw some terribly parameterized Pollock stock assessment models. And so the same thing. This is how many times faster your model would run. So thousands, really high, right? Let's ignore that's a stupid example. But here's my Pollock assessment. It runs like 200 or 300 times faster. WAM's another one we could focus on. That's like 50 times faster. I'll show you that in a second. And so I've ordered it here, obviously, as descending. So, here, these are way better. We're talking, double, half to 10th to 100th of the runtime. That's really fast. That's a huge improvement. There's a kind of a collection where it's like, it's, a little bit. And then there's two that are worse. So let's focus in on one that does better and one that does worse. And here's what I talk about. Yeah, so this optimization, calculating Q, inverting Q, all is about 1 to 2% of the total runtime. So it's very little downside of trying it. So let's take this WAM model. This is from one of their examples. I don't know if Tim's online, but it's example 13, I think. So it has 2D AR1 state transitions on log numbers at age and an eco regression. This is a complicated stochastic model. And I caveat, I did have to tinker with a couple things. But still, we're talking a pretty complicated model. So this is what the output looks like. If I use what I'm calling a unit metric, basically don't use the stand defaults. It takes 2.3 hours and I get, 450 effective samples. Now down here, I just rerun the same model. I say do sparse, 9 minutes and 900 effective sample sizes. So it's both it runs faster, way, way faster, and produces more effective sample sizes. And this is true of every stock assessment I've tried this on, which is admittedly fairly limited. Darcy, who commented earlier, we did this on his Southern Bluefin tuna model, and I think it was about the same, like a couple hours to like 10 or 20 minutes. Yeah, Cody, please.
Are any of those models simulated so you know the true, like, do you do it faster and get the right answer, or do you just do it faster and you don't know what the right answer is right now?
Well, you never know the right answer for a complicated model. So the question is, the question is this on simulated data or real data? Cody thinks that if you do simulated data, you know the true answer, and I would contend that you know properties of it. Let me take a drink.
I think it depends if you're a Bayesian or a test.
So let me answer that question by saying we're convinced that it's the same because the gradient when we use the sparse metric comes out the same as the dense metric. And asymptotic, if I run a bunch of samples on known models, it comes out the same. And so the asymptotically they appear to be the same, but it's true that we do not have a mathematical proof of the equivalency of the dense and sparse matrices as formulated here. And I'm hoping Casper can do that for us, because neither Jim nor I know how to do that. If anybody in the room knows how to do that, that'd be great. Okay, so this is it in a nutshell. So why is WAM so much faster? So this plot, maximum correlation. This is kind of, if you take a parameter and you say, among all other parameters, what's the highest correlation? And then that's a point. So each point is a parameter, and the x-axis is the highest correlation with all other parameters, obviously not itself, which would be 1. And then it's the same model, 2 different metrics. And so you can see that the correlations are the same. The metric doesn't get rid of the correlation. What it does is it allows it to sample equally well, regardless of the correlation. Look at this shape. High correlation, low efficiency, low effective sample size. This is the bottleneck of the model. This trend is what we predicted would happen, and then it's flattened because we've decorrelated the posterior. And so there are no, when I'm sampling with the sparse metric, there are no correlations. So it samples equally well for all parameters. That's why it's faster. I'm not going to get into this. Let me, how much time do I have? No, I got to go. Sorry. Okay, let's go. Here's what happens when it goes wrong. Upper right, bivariate posterior, different metrics, etc. Those are the points. The blue in the ellipse, that's Q. Q is not a good approximation of the shape. It's not linear. And the MLE is like right on the boundary of it. So when I do the rotation, which is shown here in the bottom, this is the Y space on the bottom, it doesn't look good, right? And it actually makes sampling worse. So when Q does not approximate the posterior well, it can be worse. Short answer. Yeah, I'm just going to skip through this.
Is there any way to know when you're in one circumstance or the other?
Is there a question? Is
there an easy way to know whether Q is a good representation or not?
Yeah, that's actually this plot. So this is WHAM. So this is WHAM. So these are the 4 slowest mixing parameters, and the same thing. The red ellipse there is the Q estimate, and the points to the posterior. And so we could see like the slowest mixing ones, like it's not an issue with correlation, it's an issue with scale. Pop quiz, how would you solve this? This is the estimate of Q, and it's not good, and it's slowing down sampling. How could you solve this? So here I should have said there's no adaptation of the diagonal matrix, mass matrix that Stan does. I've turned that off. If I turned it back on, Stan would then know, oh, this is quite a bit bigger. The scale is bigger, and this would be more efficient. Okay. So I'm just going to make a broad case. Like I think hopefully I've convinced you of all these things are true. These kind of hypotheses. I think we've kind of checked all these boxes. More than just nuts. Like I think sparsity is something we should all embrace. Like TMB does this well, and I think other fields and software platforms should do it. It affects a ton of stuff and improves a ton of stuff in our models. And you can read that there if you want. Yeah, I mean, there's a bunch of reasons why you can have inefficiency that I've like glossed over. Sparse nuts will not work better if the problem is not a linear correlation. Yeah, and again, it's kind of chicken and egg. It works best, and you need Q to do it. It works best when it's multivariate normal, and that's when you have Q. So it's not solving all of the problems, but it's going to work well for a large class of models. So we're working on the paper, kind of trying to figure out how to interface this still. Kind of just tinkering still, which we can come back to in the discussion if people have questions. So this is kind of what it looks like. So you can just say, TMB run example, that'll just load object in your global workspace, fit, that's it. And there's a bunch of defaults that work well. So in this case, it chose a dense metric because it was a little bit faster than a sparse one. Took a few seconds to run, and then there's kind of some helper functions to go along with it. And with that, I'm a little over time, sorry. I'll take questions, flash the references for the video, and open it up to questions, discussions, advice, whatever. Thank you.
Can you go back one slide to the sample output?
Which one?
Forward. The model, the simple model that you did.
This.
No, keep going. Yeah. The code.
Oh, the code.
Yeah.
The code. Yeah.
We just want to know what command to run.
So, you said that it chose a dense metric instead of sparse.
Yeah.
So it's doing it automatically. You're not telling it to.
Yeah, exactly. That's one of the slides I skipped. So the 5th step here is to auto detect the metric, and this is the default, which I recommend people use for most things. So basically, if you don't have Q, you just go back to what nuts does normally. You kind of back to the standard. If you have Q and you invert it and there are no correlations, they're all small, you don't need to do dense or sparse. You just do diag. And then either dense or sparse if there are high correlations, and that kind of depends on the dimensionality and sparseness of Q, which one will be faster. What I do is I just calculate both. I do an internal timing of the gradient call, and whichever one's faster is the metric that's used. So in this case, here there were high correlations, and the dense was a little bit faster, and that doesn't surprise me because it's like under 200 parameters. So
it just saves time from having the analysts look at Q themselves and be like, oh, okay.
Yeah. So it just automatically detects it for you, and and we're kind of fiddling with the heuristic algorithm for that. Maybe I'm going to leave it here. I think this is like the go-to tool for our stock assessments at a minimum. Like if we want to do this on TMB state space stock assessments, this is what we should be doing. A couple hours is ridiculous. Most stock assessments should take 10 or 15 or 20 minutes. And that's what we found kind of in the handful we've done. A couple hours of runtime is stupid. That's why I did this. It's because my stock assessment took too long to run. But I think it also applies also for spatial models. It's really, really good for spatial models. Go ahead.
Darcy has a question.
Darcy, yeah, go ahead.
Yeah, thanks, Cole. Yeah, I mean, I totally agree. When I moved from ADMB to Stan, for example, it made my models, MCMC ran in days, changed it to, hours or tens of hours, and now this has basically made it run tens of hours down to an hour or less. So it's pretty awesome stuff. I do have one question though, or something to put to you. When you're in your code, your R code, you're refitting the model, recalculating the MLE, excluding the random effects before you to calculate the Q matrix.
Yeah.
But when you do that, you don't have an option to turn the Jacobians on or off. And so, if you're doing MCMC, then you want to turn them all on and use them. But basically what you're doing is calculating an MLE with the Jacobians turned on. And I mean, I guess in some cases that doesn't matter, but it does seem to actually affect the MLE for some of the models I've been working on. I just wondered if there's any scope to, build. That's one of the things I guess I've struggled with in using TMB and RTMB is turning Jacobians on and off. It's just kind of messy. I wondered if you wanted to comment on that. Thanks.
Yeah. So the comment was on the Jacobians, and I've brushed all that under the rug. When I want to be clear though, when I'm re-optimizing, there's no Jacobian applied. That's just calling the optimizer as normal. And I've also I kind of didn't talk about this, but there's obviously parameter transforms that can be done and so forth that where Jacobians apply, and you kind of have to do that manually still. But so it's true. It's a bit messy compared to the interface for Stan or ADMB actually, where you can define like a bounded parameter or whatever. So yes, the Jacobian stuff is a bit messy and you have to do it manually. I've been really careful here though of, everything is in the inverse transformed space. So like log, not or logit space. And so there are no Jacobians. And yeah, I'm going to pump that actually. Yes, it's messy and hard to do.
All good. Thanks, Cole.
Yeah, thanks, Darcy. No, it's a valid point.
Okay, sweet. Well, I think we're pretty much out of time. So with that, give another round of applause for Cole. And thank you for everyone for coming to today's quantitative seminar. We hope to see you next week, where we'll hear from Eric Anderson on dissecting the genetic architecture of adult migration timing in Chinook salmon in the California Central Valley. So thank you all.